Welcome back. Once again, just give yourself a couple of seconds to mentally get here, so to speak. Welcome back. Oh, looks like I am not sharing correctly. Let's figure that out. Okay, there we go. That's better. We're moving deeper now today into our understanding of the tree of life. Talking now about how we use this map, or really how we make this map actually, and what we use to make the map. We're going to use an example of ground squirrels, or squirrels, not just ground squirrels. And we're going to imagine a scenario where we're interested in learning what's the relationship between this group of squirrels. We want to create a map. We want to create a phylogenetic tree that tells us which of these 3 species that I've put in this pink box are more closely related to each other than others. And so you might be wondering, if we're interested in the fox squirrel, the eastern gray squirrel, and the western gray squirrel, why is there a ground squirrel over there? That's an excellent question. The ground squirrel is what we call an outgroup. And an outgroup establishes the basic structure for our phylogenetic tree. An outgroup is a taxon, in this case a species, that we are almost completely certain, in some cases certain, is more distantly related to our taxa of interest than they are to each other. What that does is that allows us to give our tree some initial structure. So we know that we have a root, we have a lineage that leads to the ground squirrel, and then we have a lineage that leads to our 3 squirrels of interest, our fox squirrel, our eastern gray squirrel, and our western gray squirrel. What we're not sure about yet is where each of these are going to, quote unquote, sit in that branching pattern. So what is that pattern going to look like among these 3 species of interest? How do we do that? In this case, we're going to use homologous genetic sequences as an example. We're going to use the hemoglobin gene. The nice thing about hemoglobin genes is that they're very what we call conserved. As you know, hemoglobin is critical to our body's ability to carry oxygen. So as you would imagine, these genes can only undergo so many changes. So hemoglobin genes have, in the course of evolutionary time, experienced fewer mutations, fewer base pair changes than do many other genes. We've sequenced our 3 species of interest, or our 4 species of interest, and we're going to use these sequences of the hemoglobin gene to place these species on a phylogenetic tree. Most of the sequence is exactly the same. As we said, they're homologous, right? But I'm just going to draw your attention here to, in this first codon, so if you remember from genetics, our bases are going to be in groups of 3 codons, and those codons each encode their own amino acid. In the 3rd position of the first codon, you can see that the ground squirrel and the fox squirrel, so the first number 1 and number 2, here and here, both have a T. But the 2 gray squirrels both have an A. So we see a change there in the genetic sequence, and that's going to give us information. And then if we look at the third position of the third codon, we see another change where the ground squirrel and each of the gray squirrels has the same base in that third position, and the fox squirrel has a different base. And these changes are going to be the basis of how we construct our phylogenetic tree. Going back to the arrangement that I had earlier, what I've done is I've just added some symbols to indicate what bases we're interested in, just in case those colors aren't super clear and obvious. The star represents the third codon, or the third position of the first codon, and the circle represents the third position of the third codon. One's marked with a star, each correspond to the same position in all 4 species, and one marked with a circle, each correspond to the same position in all 4 species. As I mentioned before, our outgroup gives us our initial structure for our tree, and what we're figuring out is where do 2, 3, and 4, the fox squirrel, the western gray squirrel, and the eastern gray squirrel, where do they fit in relationship to each other? And what we want to do is we want to compare their bases. So these character states is what we're comparing. And we're figuring out how many changes in those bases would it take to get to these different character states, so these different sequences. We're looking for the fewest number of changes because, as I said, we know that the hemoglobin gene is very conserved. If we look at the ground squirrel, first codon, and we look at the fox squirrel's first codon, those are the same. No change there. If we look at the third codon, we have a change here. One of the bases, that third base, over the course of evolutionary time, changed in the fox squirrel. So let's say, okay, we know that this lineage came up here. And let's imagine one of our options is a bifurcation here, a split, and one of those went to the fox squirrel. If that is the case, then for this to happen, we needed one change in that lineage from, I should use black, from the sequence of the ground squirrel. So what we believe to be the ancestral sequence required one change. So we have one base that changed. And then, okay, what's happening over here? Let's look at the 2 gray squirrels. What do we have going on over here? If we look at the first codon here, oh, we have a change there. No change there, that's the same. And this, both of the gray squirrels have the same sequence. So their change is the same. So if we have a lineage that comes over here and we say, all right, there was a common ancestor that experienced that single change, and then from that common ancestor, the 2 extant species of gray squirrel evolved. For this tree that we're checking, maybe this was the way that it happened, we have a total of 2 changes. Because we had one on the lineage that led to number 2, the fox squirrel. We had one on the lineage that led to numbers 3 and 4, the gray squirrels. Total of two changes in the sequence of bases. Let's compare that to other options. That's not our only way that we could construct the tree. We could switch the order around. The numbers that these have are arbitrary. So let's move number 3 over. Let's switch number 2 and 3. We still, no matter how much we move 2, 3, and 4 around, we know that the ground squirrel is still our outgroup. So we can still construct the tree starting the same way. Cool. We can still start with the same thing. Let's have our bifurcation here again. Let's go, okay, cool. Let's go over here. How many changes from our ancestral sequence do we need to get to our gray squirrel? Let's look at the first codon. Okay, we have a change here. And then let's look at our third codon. No change here, that's the same. All right, we had to have one change to get from our ancestral sequence to our gray squirrel. Now, all right, one change there. And let's look at what's going on over here. Look at our fox squirrel. First codon is the same. Now let's look at our third. That one's different. Look over here at number 4, our other gray squirrel. Look at the first codon, we've got a difference. And then at our third codon, that one's the same. Okay, so to get from this ancestral state to each of these different base sequences, then that's going to require another 2 changes. So we have to have, blue. We have to have a change here. And we also have to have a change here. If the ancestor here, that's a good way to, here, that gave rise to this sequence experienced that change, and this one then experiences this change, then we have to have 3 changes. So that's not as parsimonious. That's more changes, which is less likely in the hemoglobin gene. Okay, so that one seems less likely than the first option. Okay, all right, let's do another, let's flip some things around. Now, once again, our ground squirrel is our outgroup. And let's think about, what if we go over here to 4? How many, what happens here? We have this one's different. This one's the same. Now let's look at our fox squirrel. That one is the same. This one is different. This one is different and the same. Okay. We need a change here. And then once again, we have 2 different sequences in this group. We have to have our change here and here. More changes, more differences than in our first option. So this one is also less likely than our first option. Oh, I forgot to put the ancestral sequence down here. Okay. So this is just an example, a made-up example of a way that using this idea that we expect the fewest possible changes helps us construct a tree. And so our most likely tree is this one, where the two gray squirrels are more closely related to each other than they are to the fox squirrel. And this process of producing trees this way, come on, is called parsimony. And the parsimony is, what are the fewest number of changes that could lead from the ancestral state to what we currently see. Oh, and I forgot to tell you, here you might be thinking, well, how do we know that the ground squirrel is the ancestral state? Which I hope you thought that, and if you thought that, that's such a great question. Or maybe you were just like, there's too much information, and so you didn't get there. But if you when you went back and watched again, you probably would. Go ahead and play with this, please. And what you'll find is that if we don't start with the ground squirrel as the ancestral state, our base number of changes is 3. So the ground squirrel is more likely to be the ancestral state. Okay. Whoops. Okay, so parsimony is least number of changes, basically. Then now we're going to, so everything we've been talking about so far is based on a tree that looks something like this. And when we're talking about heritability for our imaginary tree here, what's happening is that the genes, or the variations of the genes, are getting passed from parent to offspring. Right? This is called vertical gene transfer. Talking about something different than parsimony. That's a different thing. This is called vertical. In the video that you're going to watch in just a minute, or whenever you come back, rather than this vertical gene transfer, where genes are passed from parent to offspring, from parent to offspring, from parent to offspring, and we have this, what we call vertical transmission. What you're going to be learning about is horizontal gene transfer. What? So in that case, rather than being able to trace the lineages in this vertical fashion, you can have genes being exchanged horizontally. Ooh, that makes things interesting. Now watch a video about horizontal gene transfer, and then we're going to talk about variations on this phylogenetic theme. So ways that it can look different than this very simple pattern that we've talked about so far.